Hi there. Did you work through reference 501.1? Ira, how did you find it?
So it took me quite a while, but it was okay. I think it was fine.
Is it okay? That's good.
Sir, but I do have a question that I want to ask you. So how does a pH indicator work?
What does it mean? Do you want to know why it exhibits different colors in acid and alkali media?
Yes.
You see, Ira, a pH indicator is itself a weak acid, like HI in this case, or a weak base. This is the molecular undissociated form which exhibits one color, like red in this case, and the indicator ionic form there will exhibit a different color, like blue in this case. According to Le Chatelier's principle, the equilibrium will be driven to the right in an alkaline medium. Can you tell me why, Ira?
I have no idea, sir.
Ira, you see, with an excess of hydroxide ions present, some of the hydrogen ions will combine with the hydroxide ions to form neutral water molecules. So the concentration of these ions will be reduced, and therefore the system will drive the equilibrium to the right in order to relieve the stress, to make up for this loss. And in this case, the indicator ion, the blue, will predominate. According to Le Chatelier's principle, if we add acid to the medium, and in an acid solution, the equilibrium will be driven to the left. Can you tell me why?
No.
Well, in this case, the system wants to get rid of the excess hydrogen ions. So by driving equilibrium to the left, you'll get mostly the undissociated molecular form, which is red in this case, that will predominate. Let us look at 3 examples of pH indicators. This table shows the colors and the pHs of 3 indicators. Methyl orange is red in acid and yellow in a base. And the color change takes place from pH 3,1 to pH 4,4. Bromothymol blue is yellow in acid and blue in base. Ira, can you tell me in which pH range it will change color?
From 6 to 7.5, sir?
No, it's actually 6 to 7,6. Right, Ira? Phenolphthalein is colorless in acid and red in alkali or base. In what pH range will phenolphthalein undergo a change of color?
8.3 to 10.0, sir.
Correct. Acids and bases are such common and important substances that it is often necessary to determine the concentrations of an acid or of an alkaline solution accurately. This is the essential equation for the neutralization process, where the acid, of which the properties are vested in the hydrogen ions, is neutralized by the alkali or base, of which the properties are vested in the hydroxide ions to produce neutral water molecules. Let us say we want to standardize a solution of sulfuric acid.
Sir, can you tell me what you mean by standardizing a solution?
Here, to standardize a solution simply means that we want to determine the accurate concentration of the acid in mole per cubic decimeter by titrating it with a standard sodium hydroxide solution, for example.
Can you tell me now what you mean by titrating a solution?
Here, to titrate with a sodium hydroxide solution simply means we carefully add a sodium hydroxide solution of accurately known concentration, like 0.2 mole per cubic decimeter, from a burette, drop by drop, to the acid solution in a conical flask until we reach the end point of the titration.
And what do you mean by the end point, sir?
Here, the end point in any titration is that point where the color of the indicator just changes. In other words, after we've added equivalent amounts of the acid and the base. Let us do the experiment. First of all, I take my pipette and I draw an exact amount of the acid of unknown concentration from this container by sucking it at this end. Then we want to just get the level of the acid in line with a little ring on the stem. Not always that easy. There we are. And now we transfer this to the flask. We let the acid run down slowly because it takes time for the acid to drain properly. If we want to deliver exact amounts of acid, like 50 milliliters in this case, we must hold our pipette vertical like this, and the conical flask at an angle, and the tip of the pipette must touch the glass. We wait a little while, and then we just scrape the tip like that, and now we have an exact volume of 50 cubic centimeters of acid in our conical flask. We add our indicator, which is bromothymol blue in this case. Let's add enough to make it visible. And we titrate the acid with the alkali by adding it from the burette to the acid solution. We swirl the conical flask rapidly in order to mix the two solutions. And you can see I put a white tile at the bottom there so I can clearly see the color change when we get to the end point. We're not near the end point yet, but I can see the persistence of some blue color already. So I think we are getting closer. We are quite close now. We've got to add a drop at a time. We are very close now. There we are on the, that's right. You see, the color changes like green. That is on the neutral point. If I add one more drop, it turns blue. So what is the volume to read it?
It looks like 25 cubic centimeters. Sir.
That's right, Era. The volume of sodium hydroxide added to reach the end point is used as follows to calculate the concentration of sulfuric acid. The first step is always to write the balanced equation of the neutralization reaction. In order to find out the number of moles of the alkali, sodium hydroxide in this case, which was added to the number of moles of sulfuric acid, which is 1 mole in this case. So it reacts in the ratio of 2 to 1 moles. Yara, can you still remember what it means if we say the standard solution has a concentration of 0.2 moles per cubic decimeter?
So 0.2 moles of sodium hydroxide
that's right.
was dissolved in a cubic decimeter.
Of solution, that's right. Okay, let us make this statement here. Remembering that 1 cubic decimeter is the same as 1,000 cubic centimeters. So we can say 1,000 cubic centimeters, or 1 cubic decimeter, of sodium hydroxide solution contains 0.2 moles of the sodium hydroxide. Is that right?
Yes.
But did we use 1,000 cubic centimeters in our burette?
No, so we used 25 centimeters.
That's right. So, yes, we now want to find out the number of moles of sodium hydroxide, not in 1,000 cubic centimeters.
But in 25.
Yes. So we got to do a little proportion sum. So we say, therefore, 25 cubic centimeters of sodium hydroxide solution contains, and then we do a little sum where we invert those two quantities, write the 25 on the top, 1,000 at the bottom, and multiply it by the quantity on our right, which is 0.2. And let us say this is X moles of sodium hydroxide. We're going to use this later in our calculation. So we call it X for the time being. If I look at my balanced equation, I notice that 2 moles of sodium hydroxide reacts with 1 mole of sulfuric acid. So that's what we're saying here. 2 moles of sodium hydroxide is neutralized by 1 mole of sulfuric acid. But we didn't use 2 moles of sodium hydroxide.
We used X moles.
That's right. Yeah, so we used X moles. So X moles of sodium hydroxide is neutralized by X over 2, half that number of moles of sulfuric acid. Can you see it? The reaction ratio of 2 to 1, or X to X over 2. All right. But you know, this X over 2 moles of sulfuric acid is contained by what volume of sulfuric acid? Think of this. Just look at our sketch again.
50 cubic
Aha.
centimeters, sir.
We placed exactly 50 cubic centimeters of sulfuric acid in a conical flask. And obviously the X over 2 moles of sulfuric acid must be contained by that volume. So here we say 50 cubic centimeters of sulfuric acid contains X over 2 moles of sulfuric acid. But, of course, we're not interested in the number of moles of sulfuric acid in 50 cubic centimeters when we find concentrations. We want to know the number of moles in what volume?
In 1,000.
Correct. So we've got to do a little proportion sum again. We say, therefore, 1,000 cubic centimeters of sulfuric acid contains, and once again we take these two quantities, we invert them, and we write and multiply it by the quantity on the right-hand side, X over 2. And now we go and we substitute the value of X. Can you remember what that was?
Yes.
We found it over here.
25
That was 25 divided by 1,000. That's right.
0.2.
Correct. Okay, when we substitute that quantity there for X, 25, times 0,2 over 1,000, and we delete those two quantities, we get the concentration of sulfuric acid is 0,05 moles per cubic decimeter. This whole calculation can be done in a much more simplified way if we remember that concentration is given by the number of moles per unit volume, or the number of moles divided by the number of cubic decimeters of the solution. If we change the subject of this formula, we see the number of moles is the product of concentration and volume. So we get this formula here, where the A on top here is the number of moles of acid in a balanced equation.
And the B?
And that was 1 in this case, right? And that, of course, is equal to the product of the concentration of the acid and the volume of the acid. And at the bottom we have B, yes, that was your question, that is the number of moles of the base. How many moles did we use in this case? 2, right. So the number of moles of base here is the product of the concentration of base and the volume of base. So if we change the subject of the formula, taking this product to the top and the volume of acid to the bottom, and remembering that A is 1 and B is 2 in this case, substituting for concentration of base, our standard base solution, and for the volume of base used and the volume of acid used, we get exactly the same answer. The end point of a titration, that means when we just have a change of color of the indicator and we stop adding the acid or the base, does not always correspond to the neutral point of pH 7, where we added equivalent amounts of acid and base, because of the phenomenon of hydrolysis. Now, neutralization is the reaction between an acid and a base to produce a salt and water. Hydrolysis, however, is the reverse reaction of neutralization. We can therefore define hydrolysis as the reaction between water and a salt, or the ions of the salt, to produce the original acid and base. Now, it is very important when we have to make the correct choice of pH indicator for a given titration to take this phenomenon of hydrolysis into account. Let us look at the titration of a strong acid, like hydrochloric acid, with a strong base, like sodium hydroxide, to give us the salts sodium chloride and water. Now, if this reaction did take place, we would have had sodium hydroxide formed and hydrochloric acid formed. But since sodium hydroxide is such a strong alkali and hydrochloric acid is such a strong acid, they will both be completely dissociated in water. And since they react in the ratio of 1 to 1, you'll have the same number of hydroxide ions present as hydrogen ions in the solution. This, of course, means that the concentration of the hydrogen ions will be exactly equal to the concentration of hydroxide ions, which in turn is equal to 10 to the power minus 7 moles per cubic decimeter, and that makes the pH 7. This means that the salt of a strong acid and a strong base undergoes no hydrolysis, and the solution will be neutral at the end point. Here I've dissolved some sodium chloride in water and added some universal indicator, and the green color indicates that the solution is neutral. This is the titration curve for the titration of a strong alkali like sodium hydroxide against a strong acid like hydrochloric acid. We see here that the pH rises very slowly in the beginning as we add sodium hydroxide. But at the end point, the pH rises very steeply through several pH units. And then again, after neutralizing the acid, the pH only rises very slowly again. Any indicator that undergoes a color change in the vertical part of this graph, from pH about 4 to pH about 10, can be used in this case. Like methyl orange, undergoing a change from pH 3,1 to 4,4, or bromothermal blue, undergoing a change from pH 6 to about 7,6, or phenolphthalein, undergoing a change from pH 8,3 to about 10. What happens if we titrate a weak acid against a strong alkali? Let us look at the titration of the weak acid, acetic acid, also called ethanoic acid, against a strong alkali, caustic soda. The salt produced in this case is sodium acetate, which reacts with water or gets hydrolyzed to produce the original acids, acetic acid and sodium hydroxide. Now, since acetic acid is a weak acid, it only dissociates to a minute extent, and the equilibrium lies far to the left which means the hydrogen ion concentration will be low at equilibrium. But caustic soda is a strong alkali, which is virtually completely dissociated into ions. So the equilibrium lies far to the right, and we have a high concentration of hydroxide ions at equilibrium. This means the hydroxide ion concentration will be greater than the hydrogen ion concentration in this case, and the pH will be greater than 7. So the salt of a weak acid and a strong alkali will undergo hydrolysis, and the solution will be alkaline at the end point. Here I've added some sodium acetate to water and also added some universal indicator, and the blue color indicates that the pH is above 7. This is the titration curve of a strong alkali like caustic soda against the weak acid, acetic acid. We see that at the end point, that's the vertical part of the graph, doesn't correspond to the neutral point any longer. And to avoid an endpoint error, we must use any indicator changing color in the pH range from about 8,3 to 10, like phenolphthalein, corresponding to the vertical part of the titration curve. What about the titration of a strong acid against a weak base? Let us look at the titration of the strong acid, hydrochloric acid, against the weak base, ammonium hydroxide, to give the salt ammonium chloride, which hydrolyzes with the water to form ammonium hydroxide and hydrochloric acid. Ammonium hydroxide is a weak alkali. What does that mean? It means it only dissociates very slightly. The equilibrium lies far to the left, so we get a low concentration of hydroxide ions in solution. Whereas the hydrochloric acid is a strong acid which is virtually completely dissociated in water to produce a high concentration of hydrogen ions. The hydrogen ion concentration will therefore be greater than the hydroxide ion concentration, and the pH will consequently be smaller than 7. This means that the salt of a strong acid and a weak alkali will undergo hydrolysis, and the solution will be acidic at the end point. In this test tube, I've dissolved some ammonium chloride and added some universal indicator, and the color turned red, which indicates that the pH is less than 7. This is the titration curve for this reaction. Any indicator undergoing a change of color in this vertical part of the titration curve can be used, like methyl orange, changing colors from pH 3,1 to 4,4. Stop your videotape now to attend to worksheet 501 in your workbook. Stop your videotape now.